Hello and welcome. Let's continue with our lecture in general theory of relativity. In the last lecture, we have seen some of the aspects of covariant derivative connection and so on, though because of intermingled topic, we could not have a proper examples. We apply all these concepts to special geometry, that is S2 or sphere in two dimensions. Now, sphere is a not flat geometry. It is obvious it cannot have a one-to-one correspondence with R2. Here, the geometry is non-trivial and we can apply all the concepts related to curvilinear geometry to this example. Let's continue with the example and look at the various things which we have looked at earlier and apply them onto the sphere. Let's continue with the lecture. Let's start with the geometry of two spheres. So the line element for sphere or S2 is given by ds square is equal to d theta square sine square theta d phi square. Theta and phi are the coordinate in this case. This line element can be easily obtained by setting r is equal to constant in the spherical polar coordinate system. You have already done an exercise in which you started with the Cartesian coordinate and put the constraint x square plus y square plus z square is equal to constant and obtain this met. Now here the theta goes from 0 to 2 pi and phi takes the value from 0 to 2 pi. Sphere are a very common object. On the north pole theta is 0 and in the south pole theta is equal to pi, and then we have a theta is pi by 2 here, which we call as a equatorial plane. Now we have a phi usually anti-clockwise direction and it takes the value from 0 to 2 pi. So these are the usual coordinate system. And it's an important thing to note that the theta is equal to 0 and theta is equal to pi by 2. We have a coordinate singularity. Here there is a degeneracy that all the phi's from 0 to 2 pi maps on to single point. Theta is equal to 0 and theta is equal to pi. So this is same as coordinate singularity at the origin of a plane polar or spherical polar coordinate system. You have already done the equation of motion for free particle using a Lagrangian. Let's quickly go over this. The equation of motion for a free particle can be obtained with this Lagrangian given here. L is equal to half theta dot square plus sine square phi dot square. We have also seen that the equation of motion can be casted in terms of the geodesic equation x double dot plus gamma a b c x dot b x dot c is equal to 0. A and b takes the value of 1 and 2 for theta and phi. So usually use Greek letters for 4 dimension. Any other we use Latin index. Let's get the theta equation of motion. The Lagrange equation of motion is given by d by dt of dl by d theta dot minus dl by d theta is equal to 0. From the above Lagrangian we get dl by d theta dot is equal to simply theta dot. We also get dl by d theta is equal to sine theta cos phi and phi dot square. Putting it all together we get theta double dot minus sine theta cos theta phi dot is equal to 0. So this way we get the second order equation of motion, which we can directly compare with the above form. Now let's also get phi equation of motion. In some form it is fairly simple, in some form it is not. So idea is Lagrange equation for theta is given here, which is again simple and straightforward. We get z component of angular momentum is conserved, that is basically is the equation of motion because Lagrangian is independent of coordinate variable phi. So equation of motion is basically d by dt of sine square theta phi dot is equal to 0, which we can write in terms of the second order differential equation by expanding this differentiation. Eventually we get sine square theta phi double dot plus 2 sine theta cos theta dot cos theta into theta dot and phi dot, which we again rewrite in terms of phi double dot plus 2 cot theta phi dot theta dot. Now we have two equations of motion. Because you may ask why go through all this trouble where you have already done the equation of motion here, and especially you have already done all this in the exercise or homework problem. The answer is that formally we still do not know how to compute gamma. In this case what we do is we compare this equation of motion with the geodesic equation, which is given in terms of gamma. Compare this equation and extract the values of of gamma from this equation? We clearly see that we have a quadratic term here which is essentially this form, and then we have a second derivative which is essentially this. By comparing these two, we can get the gammas. Let's first do it for the theta equation. What we have is theta double dot minus sine theta into cos theta phi dot square is equal to 0. So we have to compare this as a theta double dot plus theta gamma theta phi into phi dot square is equal to 0. So this is the only non-vanishing term. Other terms are going to 0 because we have only phi dot square term in our equation of motion, and from this we immediately get gamma theta phi is equal to minus sine theta cos theta. On the other hand, other gammas corresponding to the theta on the upper index are all 0. So this way we have extracted the gamma. Let's go ahead and extract the gamma corresponding to the phi b. That is phi double dot is equal to gamma phi bc x dot b x dot c. This is how we got to extract this. So let's compare this straight away with the equation of motion which we got. We got phi double dot plus 2 cot theta phi dot theta dot is equal to 0. So this in fact we have to compare with the phi double dot plus 2 into gamma phi theta dot phi dot. Why this theta comes, I will let you reason that. So from this comparison, these two equations, we get gamma phi theta phi is equal to gamma phi theta is equal to cot theta, and the other gammas are 0. That is, we have phi theta and phi is equal to 0. So this way we can compute gamma for a given any metric, and it is rather interesting and much easier than the conventional way of determining. Let's see how many gammas we should have. In two-dimensional, we basically have each coordinate going 2 that and 3 indices are there, so that means 2 into 2 into 2. There are total 8 components. So best way is representing in terms of two matrices. One we call is a gamma theta bc, where B and C goes from 1 and 2, and then you have a 2 cross 2 matrix. Other 2 cross 2 matrix is a phi BC, which also takes the following form. Here we have only one term, that is phi theta phi term, not 0. Here we have a 2 because it's also symmetric. We have a phi theta phi and phi theta are non-zero and have a same value. So this we have obtained all values of gamma. Now you see that we have simply by comparison we have obtained the values of gamma on a sphere. So these techniques can be used in general. All you have to do is given a metric, you write down the Lagrange equation of motion in second order, not using conserved quantities and so on. Once you have the second order Lagrange equation of motion, you can straight away compare it with the geodesic equation which has a gammas in there, and then you can identify all the non-vanishing gamma values. Keep this technique in mind, though later in the course we will find a formal expression for gamma in terms of metric tensor only for a special geometry, what we call is a Riemann geometry. Otherwise, one has to, in principle, give the value of gamma. So now we have gamma. Let us see how the parallel transport works. We know that the change in a vector due to parallel transport is given as a delta TA is equal to minus gamma ABC delta B, it should be, and DC. So this is the change due to parallel transport. Now let's take a TA to be a vector only in the direction of angle theta. That is, TA as a component 1 along the theta and 0 along pi. And then let's say that we are doing a displacement delta xk in the direction of theta also with the small amount delta, that is 1 0 into delta. So geometrically we can now squash the phi dimension. We are not looking at it only in the some value of given phi, because phi does not also explicitly appears in any of these equations. So we have theta is equal to 0 on the north pole, and we have theta is equal to pi on the south pole. We have our vector which is pointing in the increasing theta direction, that is looking at the south pole. Let's take it on the equatorial plane, and this is a vector we have. Now we can compute. Now we also have delta A in the same direction. We are planning to move it in the increasing direction of theta, where phi is fixed constant. So that is a displacement. So we can directly substitute this value. For the delta theta, we find it is 0 because we have this one is a non-zero component of gamma, but corresponding delta is 0. So we are not getting any displacement. That means the displacement because of parallel transport is 0. Same way you can compute change in the phi component. Phi component is already 0. You can substitute in this equation and then you see that there are two non-zero terms. When you substitute, all of them gives you simply 0. In this case, delta A turns out to be 0, which indicating that when you parallel transport a vector in increasing theta direction with the component only along theta direction do not change. So it is like this vector is moving in the direction of theta, so there is no change because of parallel transport. Now the general idea here might be that because you have the metric coefficient of theta component is 1 and it essentially behaves like a flat metric, and hence there is no change in the vector due to parallel transport. It is just like using your parallelogram law, but in a slightly complicated way. You are moving in the direction of theta. Let's look at one more example where you have same vector now which is being transported in the direction of phi. It is clear that we need involvement of phi direction to have the real geometric effect on the sphere. Theta direction does not really gives any specific to sphere. It almost looks like a linear geometry. Let's look at what happens if we take the vector with the component only in theta direction and we displace it in the phi direction and see what happens in the parallel transport. The basic idea again you see here, when theta is equal to pi by 2, we see gammas all going to 0. In the first case, gamma we have is a cos theta. This term will bring it to 0. Second one is a cot theta, which will also be 0. So when angle is pi by 2, that is on an equatorial plane, all components of gammas are 0 and we will not have any change in the vector when it is transported along the great circle on equatorial plane. Again, when equatorial plane means theta is equal to pi by 2, and then the metric coefficient of d phi square term would simply become 1, and it again behaves like a flat with the constant coefficient in the metric. So this leads to almost flat geometry. Now let's take an angle theta which is not equal to pi by 2 or equal to 0, something in between, so that we can explore what is a change of vector due to the parallel transport. Here the geometry is that you have theta is equal to 0 pole here and you are looking from the top, and this circle is theta is equal to pi by 2 and you have phi going from 0 and to 2 pi. So this is the notation in this drawing. So you have vector delta A pointing orthogonal to the plane here, and then the vector TA is pointing orthogonal to this plane. That is why it is drawn as a circle and a point, which means it is going through the plane. And then we have a delta A in the direction of theta, and theta here is some theta naught which is not 0. So you can again look at in the theta direction, the change in theta direction, you can compute this and it turns out to be 0. On the other hand, phi direction, you can again compute them. These two terms, one of them would go to 0 on the virtue of delta theta is 0 and theta phi is 0, and then we have the first term which is non-zero where we have t theta and delta phi is there, and that term is a delta cot theta. Now again, when theta becomes 0, we have a problem. There is a singularity. Otherwise, this would be the change in the direction due to the parallel transport. Now we can take one full round around the theta is equal to constant, where theta is neither 0 nor pi by 2. Then you take a vector parallel transport around that circle and then come back again to 0. Then you will see that parallelly transported vector would have acquired an additional term, and that term can be straight away computed by substituting into this equation and taking around the circle. That is how you compute the parallel transport for a given geometry and given connection. Later we will see that connection can be determined from the geometry, but as of now we do not have a formal expression that we will derive in the next class. Now you have a homework problem. In this problem you have to take this case where you have a vector given by TA is equal to 1 0, and with the displacement vector delta A is equal to 0, 1 dx. So this you have to take with the angle theta not is equal to 0 and not is equal to pi by 2, and then accumulate the change in the vector t as you take one full round along phi from 0 to 2 pi. We have done the calculation bit by bit. You got to put all together and then get the final expression for this change. Now we'll see the real demonstration how these displacements look on a real sphere. The geometry of a sphere is best described with the sphere itself. The sailor earlier, couple of centuries back, had a trouble of carrying the maps. The maps, in short, supposed to represent the geometric location of the earth. Unfortunately, if you believe in non-flat earth model, or earth is spherical or close to it, then you need a transformation of each small region onto a flat space, which leads to all kind of a distortion. Classic example is the Greece land. There are various specialized maps to project each and every region. Best way is to see them on the sphere itself. Let's go on to do this. I have taken, just to demonstrate various geometry of sphere, I have taken the sphere itself. What I have here is a two spheres. This is a conventional basketball, and then last time recorded things didn't come up properly because this was a bit too small. So I got in another one, big one, so that we can have all the things demonstrated. I thought even I can write on this because it is simply a plastic, so one can clearly record everything. However, I find that my inferior quality camera and the lighting system are not good enough to show everything written on this. So we will use some other cheap tricks to make the writing cleanly visible. Okay, that is another one. This is not a conventional sphere. It is just a microphone. Because I am enlarging my screen, I cannot hide it properly. So let's have this one, this sphere, and you see that it has pole here. Now, as earlier we have referred, we have two coordinates on the sphere. One is theta, which start from pole 0, and then all the way we go to the next pole, which is at pi. So you have pi by 2 is the equatorial plane. So here in this, all the markings corresponds to theta is equal to constant. So you can see this different theta are marked. So that is a way of one plotting. But take the limit, theta goes to 0, and phi is along this direction. There is no marking corresponding to for phi here. On the other hand, on this smaller sphere, what we have is two lines. One goes through the poles. These are phi is equal to constant. So you can go all the way till theta, and all of them merge at theta. Of course, this has some fancy lines which neither corresponds to theta is equal to constant or phi is equal to constant. So you can see what those curves are. So that is not of our interest. Let us look at the theta is equal to 0. He said that there is a coordinate singularity at theta is equal to 0 because theta is equal to 0 and all phi corresponds to single point. And same way for south pole, theta is equal to pi and all phi from 0 to 2 pi corresponds to single point. This is very similar to the origin of a spherical polar coordinate system in which you have r is equal to 0 and all the phi corresponds to single point, and that is not allowed in a coordinate system. You have to have a distinct point represented in separately. So this leads to what is called conventionally is a coordinate singularity. So we will not worry too much about it. If you try to do some calculation there, it will break because of coordinate singularity. You can easily get rid of that by changing the coordinate appropriately, and nothing strange really physically happens. Here theta is equal to 0 point is as good as any point in the sphere. You know that in the sphere all the points are same, nothing is going to change. Now the next idea is to look at the vector fields on the sphere. Now here often one, because when we represent a vector field, one expects something like that, a small sphere which may be not cleanly visible because of its color, and one thinks that it is attached here at various points. So one of the difficulty is that because this sharp thing which might break the sphere and will cause a problem. So another problem is that it protrudes out the vectors should be living on the sphere. Nothing should come up. Of course, I could have written it, but somehow writing is not clear on this. This would represent a vector field. Now, to make it more clear, I have taken a small piece of paper, and then here it is far more clear. Now you can see that this is a vector field completely attached to the sphere and not protruding out. Now this vector field is basically represented by 1, 0. That is, in the theta direction, it is going 1, and in the phi direction, it does not change at all. Of course, now I am not calling this as phi is equal to 0. Now this is point is my phi is equal to pi by 2, so that the theta increases from down all the way up here and reaches here. So this is in the direction of theta is equal to 0. So if you are looking at theta is equal to same vector at different point on the equatorial direction, you see all of them are pointing towards the pole. Okay, so this goes on. You can keep moving that. And so is when you move along theta, you will see that it reaches to the point here. So this way you can move the vector field at different point. I could also have a multiple arrows representing the vector fields. These are vector fields, means the vector you already have at different points. Now let us parallelly transport some of the vector. What is the differentiation means? Differentiation means that you transport a vector from one place to another place. Now we have said that when it is transferred to another place, it somehow get rotated by some additional factor because of the curvature or the non-trivial geometry of this that we have seen in any non-inertial coordinate system and curvilinear coordinate system. It should happen. So this is what we are trying to demonstrate. In the mathematically, we have seen that when we transport this vector from theta is equal to pi by 2 to theta is equal to pi, if we transport that along keeping phi constant, we have seen that there is no difference. So that means parallelly transported vector with respect to its original component is not going to change. What does that mean? So we have a vector here at theta is equal to pi by 2 pointing at theta is equal to pi, and then we move it. Okay, we move it along like this, and then we come here to another angle, theta is equal to maybe 3 pi by 2 or whatever. Now when we reach here, this vector and this vector has not acquired any other component. That means this vector and this vectors are almost going to look same in this coordinate system. Of course, you embed in the 3 dimension, you see it is changed. But in this geometry, it is not changed. It is already looking in the same direction as theta, and then it has not acquired any component along phi direction. We have also seen that when we parallelly transport this vector on the equatorial plane and we have a theta is equal to that direction, and then when we transport it along the phi, it is not going to change at all. So that it will always remain like this. Of course, when we see from 3 dimension, we do see a change because it is from theta is equal to pi by 2, it is looking at the south pole. And this is also starting at theta is equal to pi by 2, looking at the south pole. So with respect to the sphere, the vector has not acquired any additional component. That's important. It is with respect to that geometry, not from what we see from 3 dimension. From 3 dimension, it has naturally changed quite a bit, but in the sphere itself, it has not changed. That is the intrinsic geometry. Now we have seen that if you do this transformation along phi direction, if you change it, the theta instead of pi by 2, and if you do it to some other angle, then you see that this would acquire a small angle corresponding to cot of theta. So as we go along, this would, if you move a little bit, it would acquire a small change in the component in the phi direction also, that depends on the displacement and the cot of theta at which it is kept moving, and it doesn't depend on the phi. So if you take a full round system, basically you have a small delta of phi that goes to 2 pi. So that is the extra thing only which comes in. So that is the homework problem which you are supposed to do. So this is how you see a parallel transport happening in the completely spherical geometry. So this can be done intrinsic to the geometry without referring to the any outside coordinate system. That is why this idea of a curvature is all other topic will be better understood referring to the sphere. So sphere is a very simple, you know that the sphere looks same from all direction. This means it has symmetry in all direction, what we call is a maximal symmetry, which we will refer to it little later. What is the speciality of sphere? Its curvature is constant. That is very important. So when we compute the curvature, we will also see the curvature is constant. This way, how parallel transport is understood in curvilinear geometry. So you might have intrinsic curvature, you might not have intrinsic curvature. That's a different property. It does not so much depend on the parallel transport, but you see that because how the coordinate system or the basis vector change from point to point introduces a change in a parallelly transported vector, and that depends in this case only on the phi direction, not on the theta direction. Now, if you look at the metric, theta component of a metric has a coefficient 1. So, it is almost equivalent to flat. That means that in the theta direction, geometry is like a flat geometry. It doesn't introduce us any extra component in the parallel direction. You might ask what happens on the equatorial plane. Equatorial plane is represented by theta is equal to pi by 2 and sine square theta becomes 1. The metric coefficient of phi component becomes 1, and again there is no change in the parallel transport along the phi direction. Only when we have an angle which is neither 0 nor pi by 2, there is a parallel transport acquire an additional component, because the spatial dependency of a theta component, that depending on the sine of an angle, kicks in, and that introduces the additional component parallel transport. Of course, everything breaks down when you go to north and south pole. That is because of the coordinate singularity, and the coordinate system which we use is not good enough to address the geometry at that point using this coordinate system. One may shift the coordinate system and study it. That's a different point. Let me stop here and continue in the next lecture.